Hello everyone, my name is Dongup Kwon and I'm from Seoul National University. In this talk, I will present hardware-assisted virtualization mechanism for computational storage devices. This work was done with my fellow students and my advisor, Professor Jangwoo Kim. Let me start by giving you some background information. As you can see in this figure, computational storage devices or smart SSDs integrate a data processing unit with a storage block. For example, modern smart SSDs combine NVMe SSD and FPGA implementations, and they connect them through a switch interconnect for fast data transfers between those two hardware blocks. In addition, recent work on these smart devices introduces a pipelined architecture on the FPGA for high performance and easy usability. This architecture has multiple data processing blocks, which we call operators in this talk. An on-chip switch then selectively activated some of those operators to execute user-requested applications. On the other hand, there are two ways to virtualize smart SSDs. First, software-based virtualization utilizes paravirtualization mechanisms. For example, VirtIO device drivers are used to implement paravirtualization. Through these software layers, many virtual machines can share a single physical device, and this can reduce the cost significantly in modern data centers and cloud infrastructures. And the other way is hardware-assisted virtualization. For example, an SRV-capable device virtualizes itself, and it creates multiple virtual instances. Its virtual machine then has direct access to those virtual instances and share a physical device with other virtual machines. Let's look into more details of existing software-based approaches and their limitations. The existing software-based virtualization relies on the host operating systems to emulate virtual smart storage devices. Its device emulation layer intercepts near storage processing requests and orchestrates data movement between SSD and FPGA devices. After that, the underlying resource allocation layer communicates with the physically installed computational storage devices to execute user-requested operations. However, the software-based approach cannot achieve the full potential of near-storage processing in a virtualized environment. Its CPU-centric device orchestration and data communications result in a large number of hardware-software transitions and indirect data copy through the host machine's memory. Our evaluation results show that with this CPU-centric approach, the major performance bottleneck shifts to the soft layers in a virtualized environment. Another limitation is their static resource allocation mechanism. This figure shows the example scenario. The previous SSD and FPGA virtualization studies support a VM oversubscription model, which can allocate more virtual machines than available hardware resources. However, with a static virtual machine to hardware resource allocation, some FPGA operators can be highly contended by oversubscribed virtual machines. In this figure, the first operator will be the performance bottleneck and result in many quality of service or QoS violations. To resolve this issue with a static allocation, system administrator should spend extra cost for the additional hardware resources to meet the target QoS requirement. The third limitation is their tightly coupled hardware architectures, and this architecture design will suffer from fixed provisioning and low device scalability. The left side figure shows one example. When the FPGA contains more than 3 operators, the single attached SSD cannot serve the fourth operator due to its limited bandwidth. The other example shows that when the small FPGA can contain only 2 operators, the remaining operators cannot be implemented in the FPGA. In this case, the SSD capacity and bandwidth are severely underutilized. So, we set the following design goals for a next generation virtualization for computational storage devices. First, A next-generation virtualization should support device sharing. Second, it should take full advantage of near storage processing and fast data transfers even in a virtualized environment. Third, at the same time, it should maximize the cost effectiveness. Also, it should not rely on hardwired units for high device scalability and flexible device configurations. So, in this work, we propose FlexCSV, a new hardware-assisted virtualization mechanism which maximizes the performance and cost effectiveness of computational storage virtualization stack. Our key idea is to implement the FlexCSV engine, which is an FPGA card designed for a hardware-level virtualization layer. This figure shows the FlexCSV engine architecture and its main hardware components. First, FlexCSV uploads software virtualization layer under the standard SRV mechanism. Second, it also implements dynamic resource allocation and introduces SSD FPGA decoupled architecture through PCI peer-to-peer communications. This slide summarizes FlexCSV's key ideas and benefits. First, it supports device sharing by applying hardware-assisted virtualization to both computation and storage unit. Second, it further improves the performance by applying hardware-assisted resource orchestration. Third, it achieves high cost effectiveness by dynamically constructing and scheduling virtual computational storage devices. Fourth, it provides high device scalability and flexible resource configurations with a decoupled architecture. To the best of our knowledge, this is the first work to implement the hardware-assisted virtualization mechanism for modern computational storage devices. First of all, to reduce the software overhead in computational storage virtualization, FlexCSV engine offers hardware-assisted virtualization under a standard PCIe SRV layer. By incorporating SRV, FlexCSV engine can virtualize itself at the hardware level, and its virtual instance can be assigned exclusively to the virtual machines for the direct access. Second, to offload the resource orchestration routines to FlexCSV engine, FlexCSV extends the standard NVMe protocol and defines a new command format for near storage processing. And FlexCSV engine's device emulation layer manages both computation and storage resources based on the extended NVMe commands. The figure shows an example hardware-level scheduling mechanism. First, FlexCSV engine manipulates the DMA buffer addresses of NVMe command so that the SSD can transfer the user requested data to the FPGA's memory. FlexCSV engine also enforces a correct order of computation and storage operations by controlling the target hardware unit and routing tables in a switch. Third, for dynamic hardware allocation, FlexCSV engine implements a shared operator pool and dynamically maps user requested operations onto available physical operators. In this way, FlexCSV engine can quickly capture the dynamic behavior of a VM workload and avoid the highly skewed resource usage. In the renaming stage, the operator renaming table manages the availability of a physically implemented operators so that it can dynamically allocate the hardware resources to multiple virtual machines. Lastly, we introduce a decoupled computational storage architecture for scalable real storage processing with a multiple PCI-attached card. To make a PCI-attached devices interact with the FlexCSV engine through PCI peer-to-peer communications, the host software allocated their queue pairs onto FlexCSV engine's memory region. By doing so, board-level PCI switch network deliver their PCI read and write transactions to FlexCSV engines directly. As a result, FlexCSV can mitigate the performance bottleneck at a single FPGA or SSD by flexibly combining PCI-attached cards in a server. To evaluate the FlexCSV, we implemented our prototype on off-the-shelf devices and open-source software. Our current prototype implements 8 operator slots with FPGA's partial configuration support and allows the operator to be shared by 4 VMs through the operator renaming features. Let's move on to the experimental results. In the first experiment, we measured the performance of near storage processing benchmark through existing software stacks and FlexCSV. The graph shows the speed-up values compared to the full software virtualization mechanism. Our graph shows that FlexCSV can achieve about 2 times faster near storage processing in virtualized environments over the software-based virtualization. Compared to the software implementation with the direct peer-to-peer data transfers, the FlexCSV engine still achieves about 40% speed up due to its hardware-level device orchestration. In the next experiment, we evaluate the effectiveness of FlexCSV engine's dynamic resource allocation and scheduling mechanisms. For this evaluation, we ran 4 VMs concurrently and generated the VM workload with diverse request rates. We compared 4 different resource allocation strategies: static worst, static best, dynamic, and dynamic plus partial reconfiguration. The graph shows the QoS violation ratios with the various FPGA resource contention degrees. FlexCSV dynamic resource allocation significantly reduces the QoS violation, and its partial reconfiguration support further reduce the violation ratios in every case. I would like to conclude by summarizing main points. First, we propose a fast and flexible hardware-assisted virtualization mechanism for modern computational storage devices. Next, FlexCSV provides high virtualization performance by bypassing software stacks and fully exploiting near storage processing. Lastly, FlexCSV achieves high cost effectiveness by dynamically constructing computation and storage units at minimum hardware cost. Thank you for watching our presentation.